Hey everyone, hope you're doing well today. In this video, let's talk about simplifying exponential expressions. While I already have a video on simplifying exponential expressions without fraction bars, this video is going to deal with some examples that do have fraction bars. In this particular video, let's practice simplifying the following expressions. This will be the first example we'll look at, this will be the second, and this will be the third. If these are the types of problems that you need practice with, then stick around and hopefully I can simplify down the process. To get the most out of this video, I encourage you to grab some paper, something to write with, and let's do some math together. So for this first example, we have 12 times x to the 5th power times y to the 4th power, all over 2 times x to the 9th power times y. Now the way I like to do these is start by color coding each of the pieces. These coefficients are going to work well together, as will these x's, as well as these y's. And don't forget this y in the denominator has an exponent of 1, it's just invisible. While I know there's quicker ways of simplifying this expression, I'm going to try to be as detailed as possible in showing you how all of the pieces work. Just to be super clear, I'm going to go ahead and separate this into a few different monomials. So what I did here was I rewrote this expression, but I put the coefficients first, then I put our x terms, then I multiplied by the y terms. Hopefully this might make it a little bit more easy to follow along as we're going to simplify each part on its own. This 12 and 2 have a GCF of 2, so if we divide them both by 2, 12 divided by 2 is going to be 6 on top, and 2 divided by 2 is going to be 1 on bottom. Now for the x terms, there's really 5 x's being multiplied together on top, and we have 9 x's being multiplied together on bottom, so their GCF is going to be x to the 5th power. If you divide them both by x to the 5th power, we're just going to be left with 1 in the numerator, since x to the 5th divided by x to the 5th is 1, and on the bottom, x to the 5th, if we take that out from x to the 9th, we're going to be left with x to the 4th power. Finally, looking at the y's, the numerator has 4 of these y's multiplied together, and the denominator only has 1, so their GCF is just y to the 1st power, so if you take that out from both of them, or divide them both by y to the 1st power, then the numerator is going to be left with y to the 3rd power, and the denominator is just left with 1 whole. Let's see what we're left with here. We have this 6, and then we have a 1, and we have this y to the 3rd power for the numerator, and in the denominator we have this 1, we have this x to the 4th power, and then we have another 1. Multiplying the entire numerator together and the denominator on top, we're going to be left with 6 times 1, that's just going to equal 6, and then we have this y to the 3rd power right after it. And for the denominator, we have a 1 for a coefficient multiplied by another 1, and then we have this x to the 4th power, so that's going to be only on the bottom. So if we were going to go ahead and rewrite this expression as simplified as possible, this is what we would have. We would have 6y to the 3rd power over x to the 4th power. Now, while this is the most simplified expression using a fraction bar and positive exponents, if we wanted to rewrite this using negative exponents and no fraction bar, we would have the 6 first. The x to the 4th power on bottom is going to move up and become x to the negative 4th power, and we'll be left with this y to the 3rd power as well. So this expression is equivalent to the one we just wrote, only it doesn't have a fraction bar, but it does allow negative exponents. Here's another way you could have thought about this problem. Going back to this step over here, we could go ahead and divide both of these by 2 again, which is their GCF, and we'll be left with 6 and 1, so that's going to be the same thing. So we can go ahead right away and simplify that down to just being 6. But then for these x's, what we can do is we can move this x to the positive 9th to the numerator, and that's just going to be x to the negative 9th power, right? So we can rewrite that as x to the 5th power being multiplied by x to the negative 9th power, just like this. And similarly for these y's, what we can do is we can move that y to the 1st power up to the numerator, and if we do so, what's going to happen to that? Well, this y to the 4th power is just going to stay the same, but when we move that y to the 1st power to the numerator, that's going to say y to the negative 1st power instead. So finally, if we're going to write this simplified expression here, we're going to have this 6, and then if we multiply this x to the 5th power times this x to the negative 9th power, remember we just add those exponents together as our little shortcut, and so that's going to be x to the negative 4th power. And then finally for this y to the 4th power, we multiply that by y to the negative 1st power, we add those exponents together, and that's going to be y to the positive 3 power. So that's actually what we got earlier, so this checks out using negative exponents and no fraction bars for the most simplified expression. Let's try another one together. For this example, we have 18 times x to the negative 4th power times y to the 2nd power times z to the 0th power, all over 12 times x to the negative second power times y to the negative third power times z to the fourth power. Let's start by figuring out which parts work well together. Here are our coefficients, which can be simplified together at some point. Our x's will go together, our y's will go together, and our z's go together. And again, just to be super clear in this video, I'm going to separate this into some different parts so it's a little bit easier to understand. So here we have the same expression, but I just organized it a little bit into their common parts. Let's start simplifying now. So looking at the coefficients of 18 and 12, sure, we could divide them both by 2. We could divide them both by 3, but if we can divide them both by 2 and 3, then we can divide them both by 6. So dividing 18 by 6, we're going to get 3, and dividing 12 by 6, we're going to get 2. Now for the x's, since these can be a little bit more confusing, what I'm going to do here to show you is I'm going to move this x to the negative 2 to the top, and I'm going to move this x to the negative 4 down to the bottom. Now what's going to happen when we do that? When we move the x to the negative 2 up top, it's going to become x to the positive second power, and when we move that x to the negative fourth power to the bottom, that's going to be x to the positive fourth power. So you can go ahead and move those to make those positive exponents. Now leave that alone for now, and moving over to the y's, I'm going to leave that y squared alone on top, but let's move this y to the negative third power up top to join it so it has a positive exponent as well. So we're going to leave that y to the second power in the numerator, but this y to the negative third power is going to join it and become y to the positive third power, and that's going to just be all on top of 1 since nothing's left on the bottom. And finally, looking at the z's, notice how we have the z to the 0th power, and anything to the 0th power is just equal to 1. So going ahead and simplifying this, we're just going to say that this is going to be a 1 in the numerator, and in the denominator what we're going to write is that z to the 4th that we didn't do anything with. And of course over in front, go ahead and copy that down. We simplified that 18 over 12 to 3 over 2, so I'm just going to go ahead and write that just like that. Now let's go ahead and clean this up a little bit more here. So the 3 and 2 are relatively prime, they have nothing else in common. Now for the x's, the numerator has 2 of them multiplied together and the bottom has 4, but they both have 2 of them in common. So if we divide them both by x squared, we're going to be left with a 1 on top and x squared on bottom. And the bottom has more than the top, so it should have some more at the end here. For the y's, what we can do is we can combine those together. If we go ahead and add this y to the second power, if we add those exponents when we multiply, then we'll get y to the 5th power, right? So there's a lot going on here. Let's go ahead and see if we can clean this up just a little bit more. So I'm going to keep that 3 over 2 from the beginning that we already dealt with. And then going on to the x's, right? Let's see what we have for the x's. For the x's, it looks like we just had a 1 on top, and then we had x squared on the bottom. And then moving on to the y's, I think what we said was we're going to get this y to the 5th power by adding the exponents together when we're multiplying. We just have a 1 in the denominator. And then finally, we have the z's, and we have a 1 on top, and we just have z to the 4th on bottom. So looks like there's nothing in common top and bottom. So going ahead and multiplying the numerators together, 3 times 1 times 1, our coefficient is going to be 3. And then we have this y to the 5th power. And then in the denominator, multiplying all those pieces together, 2 times 1 is just going to be 2, so that's our coefficient. And then we have this x to the 2nd power. And then finally, we have z to the 4th power. So I'm going to go ahead and write that just like this. Okay, so not using any negative exponents, this right here would be our most simplified expression. Now let's just say you had to rewrite this using no fraction bars. What you could do is take 3 divided by 2, and that would be 1.5. And then you would have this x to the 2nd power would move up to the top. That would be x to the negative 2nd power. And then we have that y to the 5th power that's already on top, so that's just going to stay the same. And that z to the 4th power on the bottom, if it were to move up to the numerator, it becomes z to the negative 4th power. So this would be an equivalent expression that means the same thing. It just has no fraction bar, but it does have negative exponents. Now, as you start to feel more comfortable with these, here's another way to think about this that may be a little bit quicker. So starting off, we said we can divide these both by 6, and if we do that, we're going to be left with a 3 and a 2. And so I'm going to go ahead and just kind of start this fraction bar at the bottom here. So we know we're going to have a 3 over 2, okay? And then another thing we can do is we go ahead and take a look at the x's, right? And so some of you like using your power rules and quotient rules, so really you can go ahead for these x's and take this x to the negative 4th power and take away this negative 2. So think about what is negative 4 take away negative 2. If you keep change flip, that's going to be negative 4 plus 2. And so that's going to be left with x to the negative second power, right? Since negative 4 take away negative 2 is negative 2. And then you can go ahead and take a look at these y's. So if you take this y to the second power over y to the negative third power, then 2 minus minus 3, or 2 take away negative 3, is just 2 plus 3. 2 plus 3 is 5, so we're going to left with y to the fifth power. And then finally, if you want to do this with the z's, that works as well. Again, you always take the numerator and subtract the denominator. So 0 minus 4 is going to be negative 4, so that would be z to the negative fourth power. So if you were to take a look at this and compare that to what we just did earlier, this is technically the same thing that's happening, right? This does equal the same exact expression. And if you wanted to move those negative exponents down to the denominator, you could do that as well. So for example, we could go ahead and take this fraction bar and keep that 3 on top, keep that 2 on bottom, that y to the fifth power just stay on top here. The x to the negative second goes down to x to the positive 2, and then that z to the negative fourth goes down and becomes z to the positive fourth power. So either way you look at it, there's several ways to kind of simplify these expressions, but just trying to give you some different ways to think about these problems. Let's try one more together. Here's the third and final example of this video. We have the quantity of 2 times x to the third power, all raised to the second power, times the quantity of 3 times y to the fourth power raised to the third power, all over the 12 times. Here's the third and final example for this video. We have the quantity of 2x to the third power, all raised to the second power, times 3 times y to the fourth power raised to the third power, all over 12 times x to the fourth power times y to the fifth power. Let's start by identifying our common parts. Here are our 3 different coefficients that we're eventually going to want to combine at some point. These x's will go together, and these y's will go together. Now, some important things that may be hidden that we might want to know is that this 2 does have an exponent of an invisible 1. This 3 also has an exponent of an invisible 1 as well. And that's important just so we don't forget to apply our exponents outside the parentheses to them. So this 2 over here, keep in mind that's going to be applied to this 2 to the first power, and it's going to be applied to this x to the third power, as well as this 3 over here. This 3 is going to be applied to both bases in this parentheses. So it's going to be applied to this one and to this one. So I like putting those 1s in just because sometimes we forget to apply the power on the outside to those coefficients as well. Let's go ahead and now apply those exponents on the outside of those parentheses to what's inside them. So in the beginning here, we have this 2 to the first power. And again, that's going to be raised to the second power. So we're going to go ahead and write that power to a power. And then we're going to take this x to the third power, and that's going to be raised to the second power as well. So I'm going to go ahead and write that just like this. Okay. Finally, we're going to take this second set of parentheses, and we have 3 to the first power. This 3 to the first power, and that's going to be raised to the third power. Okay. And then finally, in that last part of this second parentheses, we have this y to the fourth power. But again, we're going to have 3 of those, so we're going to raise that whole thing to the third power. Okay, so that's going to be the whole numerator here. We haven't touched the denominator, so I'm just going to draw the fraction bar and copy down what we have in there. That's going to be this 12 x to the fourth power here, and then y to the fifth power. Keep in mind we didn't do anything with those yet. So let's go ahead and apply these power of a power property, which is just raising an exponent to another one. So this is, remember the shortcut is we multiply 1 times 2 here. So multiplying, that's going to be 2 to the second power. Okay, that's what we're going to have first here. Next, we're going to have this x to the third power, but we have 2 of those. So if we have 2 of these x to the third powers, that should be x to the sixth power. 3 times 2 is 6 for that shortcut. Then following that, we have 3 to the first power raised to the third power. 1 times 3 is going to be 3, so we're going to have 3 raised to the third power. Finally, we have this y to the fourth power, but we have 3 of those. So if we have 3 4s, that's going to be 12. Again, the shortcut is going to be 3 times 4, and that's going to be to the 12th power. So this hopefully looks a lot cleaner than what we had just a moment ago. And in the denominator, just copying that down, we still have this 12. We have this x to the fourth power. Go ahead and write that using separation just to make it a little bit more clean so it matches the numerator as well. And then we have this y to the fifth power on the bottom. Now again, I know this is just being a little bit more detailed than maybe necessary, but I just want to be as clear as I possibly can. So I'm going to go ahead and take the coefficient pieces and put them under the same fraction bar. So we have 2 to the third power, and then we have 3 to the third power, and we have this 12 in the denominator. Those are all going to be simplified together at some point here. Next, we have this x to the 6th power, and that's going to be on top of this x to the 4th power. And then finally, we have the y's. And for the y's, what do we have? It looks like we have this y to the 12th power in the numerator, and we have y to the 5th power in the denominator. Okay. Now let's get down to the end part here. So if we go ahead and take this 2 to the 2nd power, that's going to equal 4. So I'm going to go ahead and write 4 on top here. We're going to multiply that by this 3 to the 3rd power. Now what's 3 times 3? That's 9. 9 times another 3 is going to be 27. So we have 4 times 27, and that whole thing is going to be over 12. Okay. And then the next part, what can we simplify a little bit here? Well, it looks like it has a 6 x's on top and 4 x's on bottom. So 6 minus 4 is 2. So they can both be divided by x to the 4th power. We'll be left with x squared on top and just a 1 on bottom. So rewriting that, we can say that we have a 1 on the bottom, and we're going to have x squared on top. Okay, the top has more than the bottom. And then finally, what do we have here? Finally, if we take a look at the y's, for the y's, it looks like the top has more than the bottom. They both do have 5 y's multiplied together though, so the bottom loses all of them, but the top loses 5, so it still has 7 of them. So we still have y to the 7th power. So we're going to write y to the 7th power, and we're going to write a 1 on the bottom here. Now for our final steps here, let's go ahead and simplify our coefficients. So this 4 and 12 looks like we can cross cancel. They can divide both by 4 or their GCF, so we're going to end up with a 1 and a 3 here. But it looks like we can actually cross cancel one more time. This 3 and 27 looks like their GCF is 3, so if we divide this by 3, we get 1. And if we divide 27 by 3, we're going to end up with a 9 here. Okay, so what we have here is a pretty good deal. It looks like in the denominator, we just have 1s, and that's kind of really nice because actually our answer won't have any fractions. So on the bottom, we have 1 times 1 times 1. That's really nice. In the top, what are we left with? We have a 1 times 9. And then we have this x to the 2nd power we still have, and then this y to the 7th power. So writing our final simplified expression here, this is what we'll write. Starting off, we're going to have this 9 in the front, and then following that, we're going to have this x to the 2nd power, and then finally, we're going to have this y to the 7th power. That would be our most simplified expression, and it's pretty clean relative to what we started with. Now, while I did write down a lot more detail than may be necessary, just keep in mind the big picture. If you look back at this x to the 6th over x to the 4th, 6 minus 4 does get you this x to the 2nd power right over here, so hopefully that makes sense. And similarly, when you take a look at this y to the 12th power over y to the 5th power, 12 minus 5 is 7, so we can go ahead and get that piece right over here. So eventually you don't need to write out all these extra steps, but if it was helpful just to see all the pieces and how I thought through the process, then that was the point of this video. And that just about wraps up this video on simplifying exponential expressions dealing with fraction bars. If you found this video helpful, please consider giving it a thumbs up and letting me know in the comment section down below. And as always, keep up the great work, and as always, don't forget to simplify.